So I know we've already done this page of notes, or maybe you haven't, but just to kind of reiterate it again, Newton's second law as a reminder. This is it in formula terms. In your notes, the piece of paper we glued in with all three laws on it, it was written out. This is what it is in a formula. It's essentially saying that force, acceleration, and mass are all related. As you increase force, you increase acceleration. As you increase mass, you decrease acceleration. How it's most often written is F equals ma. It's net force, not just any force. And we had discussed how 1 Newton, remember Newton is a unit of force, is equal to 1 kilogram meter per second squared. And if you notice, a kilogram is a unit of mass, and meters per second squared is a unit of acceleration. So if net force equals mass times acceleration, then it makes sense that 1 Newton would equal 1 kilogram times 1 meter per second. Kilogram being the mass, meter per second squared being the acceleration. So there's lots of relationships involved between force, mass, and acceleration. We're going to look at force and acceleration. And if you look at the pictures, a small force leads to a small acceleration. A large force leads to a large acceleration. They're considered directly proportional. And that makes sense. If you have something sitting on a table and you push it with very little force, it's not going to accelerate very much. It's not going to go very far. If you have something laying on the table, same size, and you push it with a lot of force, as hard as you can, it's going to have a pretty large acceleration until it hits something. So small force, small acceleration, large force, large acceleration. And as I said before, that means they're directly proportional. As force increases, so does acceleration. Start here. If you double the net force, then the acceleration will also be doubled. If you half the net force, the acceleration will be halved. Increase force, increase acceleration. Decrease force, decrease acceleration. They're considered directly proportional. And what you see here is a directly proportional graph. As acceleration is increasing, so is force. We have a positive slope. They both are increasing. Next up, we have the relationship between mass and acceleration. And just a little side note, in this picture, friction's not considered. But essentially, if you have something that is very small and you push it with an equal amount of force, it's going to lead to a very large acceleration. If you have something that has a very large mass, something very big, heavy, and you push it with the same amount of force you push the small object, it's going to lead to a small acceleration. So it's important to note, essentially, that in both of these pictures, force is the same, or it is constant. So if we keep force constant, and we have a small mass, we have a very large acceleration. If we keep force constant and have a large mass, then we have a very small acceleration. And then this is referred to, this relationship is referred to inversely proportional or indirectly proportional, meaning a small mass leads to a large acceleration and a large mass leads to a small acceleration. And I want you to add if net force is constant in both situations. So this graph looks a lot different than the last graph, the force and acceleration graph. Mass is the independent, or changing mass in the situation. Acceleration is the dependent. That depends on the mass. Force is constant. So as mass increases, acceleration decreases. So that's where we get the inversely proportional. They kind of do the opposite of each other. So if net force remains the same, and I double the mass, then acceleration is halved. So let's think of your planner and your science textbook. If I apply the same amount of force to them, which one will accelerate more? It's going to be your planner, has less mass. So they are indirectly proportional or inversely proportional. The more mass, the less acceleration. Last one is the relationship between force and mass. Here's the title. Force and mass, just like force and acceleration, are directly proportional. A large mass leads to a greater net force, and a small mass leads to less net force. So, if I have, let's go back to the planner and the textbook. Which one do I need to add more force to make them accelerate at the same rate? You're going to have to add more force to the textbook because it's heavier. So more mass requires more force. And again, I want you to add a large mass leads to a greater net force and a small mass leads to less net force if acceleration is kept constant. Or if you want the same acceleration. So double the mass, you have to double the force to get a certain acceleration if you want the same acceleration. This kind of just illustrates that, pretend we have our planner and our textbook again. The small ball is the planner, the large ball is the textbook. To get them to accelerate at the same rate, you need to apply a small force to the small mass, and you need to apply a large force to the large mass, and then they'll accelerate the same. As you notice, they are directly proportional. Large force, large mass. Small force, small mass. Same acceleration. And then we come to computing Newton's second law. This is very similar to the other problems we did in kinematics. You do not have to write down this, remember, but do take note of it. This is only applied when there's an unbalanced force, because remember, unbalanced force means there's a net force present. If it's balanced, then there's no acceleration, and the net force would equal 0. So it only occurs when there's an unbalanced force. What it's kind of saying is net force equals mass times acceleration. If the forces are balanced, then there is no change in velocity. If there is no change in velocity, that means acceleration equals 0. And if we substitute this in, acceleration equals 0, no matter what, anything, that's the 0 property, anything times 0 means net force will be 0. And if that net force equals 0, then that means forces are balanced. So really this formula only applies when there's an unbalanced force occurring. So I'm only going to take you through one example. Write down the problem if you want and take note of the format. And we're going to use the same strategy, the guess. So a book with a mass of 2 kilograms is pushed along a table. If the net force acting on the book is 1 Newton, what is the book's acceleration? Let's draw our triangle. We know that mass equals 2 kilograms. And we know that net force equals 1. Our unknown is acceleration. What is the book's acceleration? Our equation for acceleration is net force over mass. If we substitute it in, we have acceleration equals 2 kilograms divided by, acceleration equals 1 Newton divided by 2 kilograms. And if you solve that out, acceleration equals 0.5 meters per second squared. And tomorrow we'll be doing pretty much the whole class these types of problems, but I just wanted to give you some background on the exact format of how to do them.